Can you see my slides?
Yes, sir.
Yes.
Okay, fine. So in last lecture, we talked about the basics behind the subject of heat transfer, and there we mentioned that the three basic modes of the heat transfer are simply convection, and radiation, right? And once again, I am putting this definition of heat or heat transfer on this screen intentionally so that you should not forget what is heat transfer or what is heat basically, right? So once again, I am repeating the heat transfer or heat is thermal energy in transit due to special temperature difference. It's, temperature difference with respect to the space. What is called space. Fine. So as long as there is temperature difference, the heat transfer will take place, right? So the basic requirement for heat transfer to take place is the temperature difference, right? So temperature difference is the driving force for the heat transfer. And I think in last lecture we talked about this rain falling from the cloud example, right? And I hope by this time you are very much clear with this definition of the heat or heat transfer, right? So moving further, the modes of heat transfer, as I mentioned before, the basic mode of heat transfer, the first is conduction. And what is the condition in case of the conduction heat transfer is the medium is stationary, means your medium is not moving. For example, if I take solid bar like this, solid bar, and if I apply some heat to one end of this bar, then we know the other end of the bar will also get heated after some time, right? So the heat will transfer from this end to this, and this is happening without the moment, appreciable moment of the material medium, right? So the medium is stationary in case of conduction. Clear? Is it clear? Now,
Yes, sir. Yes, sir.
now the second mode of heat transfer is the convection. Convection. Now, what is the essential requirement for convection? So there should be the combination of a surface, let us say a flat plate like this, surface like this, and a moving fluid. So suppose if you have the hot plate where you are applying some heat to this plate, the plate is heated, and there is some fluid which is coming in contact with this plate. So then there will be the heat transfer taking place from this plate to the surface, fluid which is in contact with the plate. So this kind of the heat transfer we classify it as a convection. So in convection heat transfer, the requirement is you should have the surface and some sort of moving fluid in contact with the surface, right? So reverse is also possible. You may have the hot fluid here coming in contact with the cold plate, then the heat transfer will take place from the hot fluid to the cold plate. So this is also possible. Right? Depending on which temperature is higher, the direction of the heat transfer will be decided, whether it is from plate to the fluid or from fluid to the plate. So both things are possible. Convection. So essential requirement of convection is we should have the surface and it should be in contact with the moving fluid, right? Now, what kind of the fluid movement is there? Whether the only molecules of the fluid are moving, or is there a bulk fluid motion as such? So depending on that, we will classify whether it is the natural convection is there or the forced convection is there. Fine. Advanced mode of heat transfer is the radiation. Radiation. Now, what is the essential requirement for radiation? We'll just go through the statement. So, in case of radiation, energy is emitted in the form of electromagnetic waves. So, this is you must have studied in 12th physics, the electromagnetic wave theory, or simply wave theory, how the energy comes from the sun to the earth. We know we classify it as based on the electromagnetic wave theory, and there is one more theory called as the photon theory. So two theories are still in literature. We say the energy from the sun, the energy which is emitted by the sun in the form of a radiation will come to the earth either by the electromagnetic waves based on the wave theory, or in terms of the photons or the bundles or the packets of energy based on the photon theory, right? And the most important part in case of radiation is this does not require any kind of the material medium in between. So without intervening medium, so you need not have the medium like in case of convection you have the fluid in contact with the surface. So here if you have the two surfaces like this, and if there is no material medium in between, still there will be the heat exchange taking place between these two surfaces in the form of the net radiation heat transfer in the absence of material medium. In fact, I would say if there is no medium present between these two surfaces, then it will be more effective. The heat transfer will be more effective by radiation. So the radiation does not require any material medium for energy transfer to take place. Clear? Is it clear? Okay. So shall I go ahead?
Yes, sir.
Yes, sir.
Now moving further, again I am carrying the same definition as it is. Now we'll talk about these three basic modes of the heat transfer one by one. Now what you see on the screen is, on the left hand side, we have the case of a conduction through a solid or a stationary fluid. So either assume this as the solid, this as a solid slab, whose this left face is at temperature T1 and the right face is at temperature T2, right? And the condition is given T1 is greater than T2, right? Or you can assume this gap is filled with some sort of fluid also, no? That is also fine. So time being, I am considering this as a solid slab. Temperature T1 is of the left face, and the right face temperature is T2, and T1 is greater than T2, right? So what will happen is the heat transfer will take place from the left face to the right face because temperature on this side is higher. If you look at the diagram carefully, you will find that the region on close to this side is dark. It's dark shaded compared to this. Getting me or not? So this is this has got more shade compared to this side. So this itself indicates that the heat transfer is taking place from the hotter surface to the colder surface. Clear? So
Yes.
if I assume that there is let us say the linear temperature variation, then I can plot the temperature distribution between these two faces of the slab as well. So I know the temperature T1 is more. So if I take this as a middle plane, I may draw it like this. So temperature on this side is higher, right? And the temperature on this side is lower. So I can draw this kind of the temperature distribution. So when I come from left to right face, the temperature is decreasing. So closer to the left wall, the temperature is more. Here it is the highest T1. And as you go along this x direction, you will find that the temperature is decreasing, and here the temperature is lowest. So the overall temperature difference for this heat transfer to take place by conduction is this T1 minus T2. I am writing it as mod, or if you write in terms of the gradient only, you may write it like this: T2 minus T1. So the final temperature minus initial temperature, you may write it like this. Fine. So the overall temperature difference, I am just writing delta T for it. So for me right now it doesn't matter whether I write it as this or as like this. So I will call it as a delta T, overall temperature difference. Clear? So now in this case there is no material motion involved here. So the solid particles will remain in the position where they are, and even though they are at their actual position, still the heat transfer is taking place through this material, right? So this is case of a conduction through a plane slab. You can call it as a one-dimensional heat conduction in this direction. So I am using the symbol Q double dash. This indicates the flux. I will call it as a heat flux. Yes. You can note down it later on. I'll project what is the symbol I'm using for what term. So as and when required, you can note down. And this shows the direction of the heat transfer from left face to the right face. So remember, the direction of the heat transfer is always from the high temperature to the low temperature, because heat is transferred from higher temperature to the lower temperature, irrespective of your orientation. Orientation of your slab, it will be always transferred from high temperature to low temperature. So direction of the heat transfer will be decided on based on what? The temperatures. Is it clear?
Yes, sir.
Yes, sir.
यस सर सर आपने वो हीट फ्लेक्स क्या लिखा है
Heat flux. See, I am using some symbol. See, we use Q for the heat in case of thermodynamics, right? Correct?
Yes, sir.
So I am going to use Q dash, let us say Q dash, for the rate of heat transfer. Rate of heat transfer. Or I may use simple Q for the rate of heat transfer. Means heat transfer per unit at time. Fine. So heat flux is the heat transfer per unit area. This Q double dot, I am going to call it as Q by A or Q dash by A. So this will be in heat transfer, let us say in watt rate of heat transfer, and this area will be, let us say, in meter square. So the unit of heat flux will be the heat transfer, rate of heat transfer per unit area. So it will be watt per meter square. Right now you need not have to bother about all this. You will come to know maybe in next 2-3 slides what we mean about these notations, Q double dot or Q dot or Q. All that you will come to know in 2-3 slides. Fine. So time you just remember, this is case of a simple one-dimensional heat conduction through a plain slab having the temperature T1 on left hand side and temperature T2 on the right hand side of the slab, where T1 is greater than T2. Clear? Now take down the next example, which is of convection. Now we will talk about the convection from a surface to a moving fluid. So here you can see there is a hot plate, that's why the shaded region is shown. High temperature means it is high temperature region. So Ts is the temperature of the surface, right? And there is a moving fluid which is passing over this plate or a surface, and the temperature of the moving fluid is T infinity. Now see, the T infinity is less than Ts, or Ts is greater than T infinity. You can see from the shades also, it is clear. So this fluid is moving over this surface. So what will happen? Heat transfer will take place from this hot plate to the moving fluid, right? And this Q double dot is nothing but the heat flux, which is passing from the plate to the fluid. So the direction of heat transfer. So what will happen if I say that the temperature of the fluid is more than the temperature of the surface? Then the heat transfer will take place from fluid to the surface. So the direction of heat flux will be opposite to this. Clear? So this is subjected to this condition, that surface temperature is more than the ambient fluid temperature. Clear?
Yes,
so
sir.
heat will always be transferred from high temperature to low temperature. Remember this. Clear? Okay, now the last example of the radiation. So now here you can see the title. What they have written is the net radiation heat exchange between two surfaces. Now why the net radiation heat exchange? Why the net radiation heat exchange? Because we know any surface which is at non-zero temperature will emit some sort of radiation, right? As long as it is at non-zero temperature, it will emit some sort of radiations, correct? So we have the two surfaces now, the surface 1, which is at temperature T1, and the surface 2, which is at temperature T2. And looking at the shade, you can say the T1 is greater than T2, correct? Get me or not?
Yes, sir.
Yes, sir.
So what you see is this surface is emitting the radiation. This is the direction of the emission in the whatever possible direction they have shown, the emitted radiations from the surface. So Q1 double dot is the radiation heat flux coming out from the surface 1. Similarly, Q2 double dash is the radiation heat flux coming out from the surface 2, right? And as we said, the net radiation heat exchange between these two surfaces Now, depending on whether the temperature of this is more than this, which is the current scenario where T1 is greater than T2, then you will find out what is the net radiation heat flux. So it will be the difference of these two. So right now the net radiation heat flux will be from surface 1 to 2. Whereas if I say temperature T2 is greater than T1, then the net radiation heat flux will be from surface 2 to 1. Is it clear? The net radiation heat flux or net radiation exchange between two surfaces. So I have to find out the net difference between these two emissions. So this is simple case of the conduction, convection and radiation. Now try to connect these examples with the previous slide. So for example, in case of conduction, we said that the stationary material medium is there. So if you consider this as a solid, let us say the material medium is stationary, it is not moving, right? So if you consider the second example, what we said in case of convection, we have the surface which is in contact with the moving fluid. So this meets the criteria of convection. And what about the last one? So here we said the radiation is in the form of electromagnetic waves, right? And it does not require any material medium in between. So even if you have the vacuum here, then also the radiation heat exchange will take place. In fact, I would say in case of vacuum, it will be more effective, the radiation heat exchange. Clear? Because it will not add any resistance to the heat transport by radiation. Now, can I go to next slide?
Yes, sir.
Fine. Now, we will see one by one what is the mechanism of conduction, physical mechanism of conduction, then the physical mechanism of convection and physical mechanism of radiation. Fine. Now, just go through the bullets. Number one, see the conduction is the atomic or molecular activity, means it happens at the atomic level. So if you take the example of that slab itself, then I can show the particles or the molecules of the material of the slab like this, and the conduction is happening at this level, atomic or the molecular level, right? So because these are not moving, these molecules or the particles are not moving or not leaving their place, right? So they are at their location and still they are transferring the energy further, or transferring the heat further. So it is an atomic or molecular activity, conduction. Fine. Then second point, the transfer of energy from more energetic to the less energetic particles will take place without movement of the particles. So the more energetic particle will give the energy to the less energetic particle, and this is how the whole heat is transferred from one end to the other end in that example of the slab. Now look at this. So what you see on the screen, can you just try to understand this diagram? See, if you understand the diagram, your 50% work is done. Huh? So you tell me, what do you see? Assume there are two parallel surfaces or flat plates. One is at the bottom having temperature T2 and the another at the top having temperature T1. So T1 is the temperature of this face, let us say, and T2 is the temperature of the bottom face. Now looking at the shade, you already have understood that this is hot compared to this. So here it is written T1 is greater than T2. And let us assume this gap is filled with some sort of gas, let us say, or air, for simplicity you can say. So this gap is filled with the gas. And what you see, these circles are nothing but the gas molecules. Let us call it as a gas molecules. Fine. Clear? Now this is drawn on what you can say the what you can say these activities are taking place at very micro level, but we have seen the, we are trying to show the exaggerated view of this, exaggerated view, right? And what is written here, you understand this, there is no bulk or macroscopic motion of these gas molecules. Now what we mean by bulk or macroscopic motion? What do you mean by macroscopic motion? You must have studied in thermodynamics. What is macroscopic? What is macroscopic?
We do not study at the particle level.
So you take what you can say, the average effect of the large number of molecules together, right, in macroscopic approach. Whereas microscopic is at the molecular level, means you will try to trace each and every individual molecule, right, in microscopic approach. So what is happening here is there is no bulk or macroscopic motion of the fluid. Means if I consider large number of molecules like this, so they are not moving together, right? So if such a large number of the molecules are moving together or at a time, I would call it as the bulk motion of the fluid. Clear? Bulk motion of the fluid. But this is not happening here. Is it clear?
Yes.
But still you will find that the heat is transferred from this hot surface to the cold surface. Now this is happening at the atomic or the molecular level. So the molecules which are having more energy, high energy molecules, they are exchanging heat with the low energy molecules. So above this dotted line you will find these are hot molecules, you can call it as, and as you go down the temperature is shown less. So here you will find that they have very less temperature, close to this T2, right? Hear me or not? And this is happening at micro level. You cannot just imagine this with our naked eyes. This is happening at micro level or atomic level, molecular activity. Fine. So what we can say is, let us say the temperature here is T1, and if I show this temperature is T2, and this is how the temperature is varying. So I can take some mid plane like this, imaginary, the horizontal line at let us say the location x0. So this is x-axis. So I am taking some distance x0 from the axis here, and I will show the mid plane like this. And if I see what is happening at this imaginary mid plane, I can say that the heat is getting transferred from this region, which is at the more energy level. Heat is getting transferred to more energetic region to less energetic region. So that's why this arrow is shown. So QX double dash, Q double dash indicates the heat flux, X indicates the heat flux flowing in the X direction, which is this direction, X direction. So the net, so the heat transfer by conduction will take place from this top side to the bottom side. And this is the temperature profile, how the temperature will vary if you go in downward direction from this top here. Clear? So this is explained considering the gas molecules here, because you should not be under impression that the conduction takes place only in case of solids. So conduction may take place in case of the liquids and gases as well. Is it clear? The mechanism of conduction. So it is molecular activity. Remember this thing. It is a atomic or molecular activity, and the heat transfer will take place from more energetic particles to the less energetic particles. Clear? Now, the same diagram I am carrying forward. I already explained this in the previous slide, but still you just go through these bullets. Just read what they have written. So the first bullet or first point, the transfer of energy from more energetic to the less energetic molecules will occur. And how this will occur? Because these molecules will come in contact with each other, they will collide with each other, and this is how the energy is transferred, right? And this is happening at molecular level. You cannot just visualize it by naked eyes. Now this will be true even in the absence of collisions. Now let us say there are no collisions happening here. So the molecules will be crossing this dotted line, imaginary line, which we have assumed. So this is what they have shown, that they are crossing the dotted line, molecules. So if they go in higher energy region, naturally they will have more energy. And if the molecules which are in the higher energy level, if they go down, they will lose their energy. They will give it to the molecules which are at the less energy level. So this you can imagine. Second point. So even if they are not colliding, So they will cross this line, imaginary line, and still there will be the heat transfer taking place. Now what we do in general is we associate the temperature, at any point with the energy of gas molecules in proximity to the point. Now what do we mean by this? Associate the temperature at any point with the energy of gas molecules in proximity of the point. So suppose if I want to tell what is the temperature at this point, so what I do, or what I am supposed to do? So I will see what are the molecules which are in close proximity of this point. So let us say these are the molecules, right? And then considering the temperature of all these molecules, I will set some temperature for this. So I will say the temperature at this point is based on the temperature of the molecules like this. So I will associate some temperature T for this one based on the molecules which are surrounding this. This is what this bullet means. Fine. Then the next point, this energy is related to the random translational motion. This is important word. Translational motion means if they are crossing this imaginary line like this, so it is a translation motion, as well as the internal rotational and vibrational motion of the molecules. Means they are at the same place and still they are vibrating, and they are not leaving their space but vibrating at that place itself or rotating. So that will also constitute to the heat transfer or the energy transfer. Clear? Now just read these 3 points and it will be clear how the conduction will take place. So what is the first point? The net transfer of energy in the positive x direction will take place. I already explained this. So this is shown here. The net radiation, the net transfer of energy will take place in the positive x direction. This is positive x direction. Then second, the collision between the molecules will enhance the energy transfer. So if there is collision between the molecules, it will enhance or increase this the rate of heat transfer. We can call it as, or it will increase the effectiveness of your heat transfer if there are collisions. Right? Then last one, we may say that the net transfer of energy by random molecular motion as a diffusion of energy. This word you should remember. The energy transferred by random molecular motion, is called as a diffusion. So collision is different word and the diffusion. So in case of diffusion, the molecules are not colliding with each other, rather they are moving randomly through this space, and this will also contribute to the heat transfer, right? Is it clear? Hello?
Sir, sir, the particles from the lower side of the temperature, like from the T2, can they cross the dotted line and cross the T1 side?
This is what is shown in the diagram. No? Both ways is possible.
Sir, so the energy of the particles will increase, right? From the lower state to higher state, okay.
Correct. See, the molecules which are at higher energy level, they will give their energy to the molecules which are at lower energy level. And this exchange will go on as long as the temperature difference exists, T1 and T2. This exchange will continue. Clear? Now
Yes,
this is an exaggerated view. This diagram is exaggerated view. This is happening at the molecular level. Only to make you understand how the conduction takes place, we have taken this example. And you should not be under the impression that the conduction only takes place in case of solids. It may be more effective in case of solids, but it doesn't mean that conduction will not take place in case of stationary fluid or even the gas also, right? It will happen. Maybe the rate will be low, the effectiveness of heat transfer may be less, but it will happen. Fine. Now, So in last example, we talked about the conduction in case of gases. Now, how the conduction will take place in case of liquids and solids. So what is the mechanism of the conduction in case of liquids and solids? Note down all the words which I have highlighted in the last slide, like collision or the random molecular motion or the rotational and vibrational motion, or what is diffusion. Note down all these words. All these words will help you in describing the mechanism of heat transfer by conduction in case of gases. How the conduction will take place in case of liquids and solids. Just go through this. So in case of liquids, the molecules are more closely spaced. We know this. And the molecular interactions are much stronger compared to the gases, and they are also more frequent. Clear? Molecules are closely packed and the molecular interactions are stronger and more frequent. Right? Solids. Now what happens in case of solids? Now still the molecules are more closely packed compared to liquids and gases. Right? Now in case of solids, the conduction may be attributed to the atomic activity, right, in the form of lattice vibrations. So if I take the example of that slab itself, and let us say I'm taking the, I'm talking about the solid at this place and that too at the atomic level, then this particle may be vibrating here itself, right? So the lattice vibrations will contribute to the heat transfer by conduction in case of solids. This word is important, lattice vibrations, or we call it as a lattice waves also. So the particle is there itself, but it is vibrating and still it is giving energy to the surrounding atoms or the molecules which are at the less energy level, right? Lattice vibrations. Now, so the solids I am going to call for divide it further in case of the electrical conductors and electrical non-conductors and electrical conductors. Now in case of electrical non-conductors, how the energy transfer will take place? So the energy transfer is exclusively via lattice vibrations or lattice waves in case of electrical non-conductors. Clear? And in case of the electrical conductors, the energy transfer is also due to the translational motion of the free electrons. And in case of conductors, the free electrons are there, right? So they can acquire the more energy and they can go to the next level. We know that you must have studied it in electrical engineering, right? So in case of electrical conductors, the heat transfer by conduction will be dominated by the motion, translation motion of the free electrons. So both these mechanisms may be present at a time. One is this lattice vibrations or lattice waves, and second is the translational motion of free electrons. So in case of the electrical conductors, the mechanism of conduction is dominated by this one, and in case of the non-conductors, the heat transfer will exclusively take place through this mechanism, which is the lattice waves or lattice vibrations, because there are no free electrons in case of non-conductors. No? So this mechanism is not there for the non-conductors. However, in case of electrical conductors, both things are working together, but it may be dominated by this mechanism. The heat transfer may be dominated by the translation motion of the free electrons. Clear? Hello, is it clear?
Yes, yes.
Yes, sir.
Can I go to next slide now?
Yes.
Now, we'll introduce the first law in case of heat transfer, the Fourier's law. Now, what is the statement of the Fourier's law? I want you to write it as it is. Take time and write the statement of the Fourier's law. Each and every word in this statement is important. Even if you miss single word, it will lose its meaning. So in a material in which the temperature gradient exists, in a material in which the temperature gradient exists, the heat flux, so I am using Q double dot. The heat flux means the rate of heat transfer per unit area. Heat flux due to conduction. Now this is the Fourier's law is for conduction. So sometimes you will find in book they have mentioned that Fourier's law of heat conduction, they say Fourier's law of heat conduction. So in oral I will ask you what is how you apply the Fourier's law in case of convection. You should not get confused. You should remember that it is applicable for conduction. So the heat flux due to conduction in any direction is proportional to the temperature gradient in that direction. Heat flux in any direction is proportional, or you can say directly proportional, whatever you want to call it as, to the temperature gradient in that direction. So this is the most simplest form of the or most simplest statement of the Fourier's law of heat conduction. So in a material in which temperature gradient exists, the heat flux due to conduction in any direction is proportional to the temperature gradient in that particular direction. So if I say x direction, I am talking about the x direction, the heat flux as well as the temperature gradient in x direction. If I am talking about y direction, the same is true for y direction, or similarly for z direction as well. Clear? So I hope you must have noted down this statement. Noted it or not?
Noted.
See, whenever I ask you to note down something, note down, because either it will be asked in examination, the theory examination, or in oral also, right? So the moment I say note down, it means it is very important part. You should remember this. Okay, now how to represent this Fourier's law mathematically? So I am writing Qx double dash. So Q double dash is the heat flux, X is for the direction. So this is the heat flux in X direction. Heat flux by conduction in X direction is proportional to the temperature gradient along that direction, X direction. So that's why I have written dt by dx, the temperature gradient along that particular direction. Suppose if I am writing it for y direction, how will I will write? So I will write Q double dot y is proportional to dt by dy. I will write the temperature gradient along y direction. So same way for z direction, I can write it like this, dt by dz, right? So Qx double dot or Q double dot x is proportional to dt by dx. Now I am going to take out this proportionality and introduce one constant. So I have written Qx double dot is minus k dt by dx, where this proportionality sign is replaced by this k, symbol k. Now what is k? This known as the thermal conductivity of the material medium. You will note down all the notations after some time, but let me just finish the writing the expression. So Qx double dot is minus k dt by dx, and then we know that the heat transfer, now I am saying Qx is the heat transfer, the rate of heat transfer along x direction. So this is Qx double dot by A. So Qx into A is nothing but Qx double dot. This I am going to put here. So Qx double dot is replaced by A into Qx. So A into Qx. And then that A is taken on the right hand side and written as the multiplying factor for this term. So this is how I am writing this expression. Clear? Qx is minus Ka dt by dx. Now why the minus sign is there? Minus sign is not for this K, remember. K is called as the thermal conductivity of the material, and it cannot be negative. It cannot be negative, and it is not, it is a non-zero quantity. So you may find the values of K like 0.2, 0.3 or 0.05, 0.003, something like that. But it is some non-zero positive quantity. The thermal conductivity is not the quantity which has got the minus sign. Clear?
Sir,
बोलो.
sir, Q double dash x is equal to Qx upon A आएगा ना?
Q double dash.
Q double dash x should be equal to Qx upon A आएगा ना?
Just a minute. Q. I wrote it in the wrong sense, right?
Yes
This is
sir.
what you are saying, ना?
Yes sir.
हाँ, ये
Yes,
notation
sir,
उल्टा हो
minus
गया.
k by a
हाँ,
आएगा.
ये notation उल्टा हो गया, ऐसा है. See, this is the heat flux, which is the rate of heat transfer per unit area. ये उल्टा लिखा है. I make the correction. See, the heat flux is the rate of heat transfer per unit area. Write it like this. Qx double dot is Qx by A, and then put it here. Here. So if you put it here, then A will be taken on the right hand side. It will be multiplied to this. I used the wrong notation. Change it. Fine. So we have defined the Fourier's law using the heat flux like this, and then we converted this expression to this form where the rate of heat transfer is given as Qx is equal to minus Ka dt by dx, right? So in few books you will find, especially the Indian author books, you will find they have mentioned the Fourier's law as they say that the rate of heat transfer is directly proportional to the temperature gradient along that direction, and also proportional to the area perpendicular to the direction of heat transfer. This is what they say. So this is how the definition of the Fourier's law of heat conduction is given in Indian author books. So they say the rate of heat transfer is proportional to the temperature gradient along that direction, and is also proportional to the area normal to the direction of heat flow. Remember this, area normal to the direction of heat flow. So in case of slab, if I have a slab like this, then this area heat transfer is taking place in this direction. Then I am talking about the area which is normal to this direction. Means if I try to draw the 3D diagram like this, so I am talking about this face area, this face, backside face. So this is A, the area of heat transfer per unit. Clear? Is it
So
clear?
what was the reason for negative k? Negative.
K is not negative. K is not negative. The negative sign is used to make this heat transfer or a heat flux positive in positive x direction. Means
So
we know.
dt will be negative.
What?
dt will be negative.
What dt? See,
Yes,
the
sir.
temperature gradient, it depends on how you are taking the sign convention. So there is one more slide, maybe after this slide, where we have used the different axis system, like the x direction, positive x direction is taken on the right hand side. In some examples, it is taken on the left hand side, and then you will try to relate all this direction of the heat transfer, then the gradient, right? So in general, if I say this is our x direction, temperature is going down like this. This is temperature T1 and this is T2. Fine. So if I am talking about this direction, how I write the gradient? I write it as final temperature minus initial temperature divided by this dx. So which is, let us say, if it is x, the distance. So I'll write it like this. So this is how we write the temperature gradient, right? So if I talk about the direction of heat transfer, we know that the heat is always transferred from high temperature to low temperature, right? So if I take this convention into account, then the dt by dx will be always negative, no? Or not? Get me or not? dt by dx will be always negative.
Yes, sir.
So that negative into negative will give us the positive sign. So we want the heat flux positive in positive direction. So this minus sign is introduced here. We want the heat flux positive in positive x direction. Clear? Okay. Note down all these notations. So what is Qx double dot? Is a heat flux, which is nothing but the rate of heat transfer per unit area. Unit is watt per meter square. What is this dt by dx? Is the temperature gradient along x direction. The unit will be the Kelvin per meter, or In some books you will find degree centigrade per meter also. Both units are same. Huh? Reason being, this is delta T in the numerator here. So whether you take this temperature difference in degree C or the Kelvin, it doesn't make any difference. It may not. Hello.
Yes, sir.
So these two units are used interchangeably. Huh? Kelvin per meter or degree C per meter, both are same. Can be used interchangeably. Now what is Qx? Qx I am using as the rate of heat transfer. Qx is the rate of heat transfer. The unit is watt. So Qx is nothing but the Q per unit time. So this is given in we know this joule, right, or kilojoule. We have studied in thermodynamics, right? And if this is calculated per unit time, then this will be kilojoule per second or joule per second, which is nothing but watt. So this is the rate. Rate means per unit time. So Qx is the rate of heat transfer or the heat per unit time. So that's why unit is watt. Clear? And the last term, K, small k, this is the thermal conductivity of the material medium, whose unit will be watt per meter K. Now how will you get this unit watt per meter K? Just keep K on one side and then write this Qx by A dt by dx, or let us keep the minus sign also, or you can write it like this and then find out the unit for K. So this Qx is given in, what is the unit for Qx? It's watt, right? What is the unit for area? Meter square. What is the unit for dt by dx? It is Kelvin per meter, and if you solve this, you will get this unit. So unit of thermal conductivity is watt per meter K. Note down this. Is it over?
Yes, sir.
Done, sir.
Done. Very good. Okay, moving further. Now, this is very important. Now try to connect this diagram with the explanation which I have given while talking about the Fourier's law of heat conduction and that minus sign in the Fourier's equation. The sign convention which we used in case of the conduction heat flow. Now there are two different diagrams on the screen. I want you to draw these diagrams. You will not find these diagrams in or the explanation of the convention in most of the books on heat transfer. You will not find this. So draw this diagram. So we have the temperature axis, this vertical axis, and the length x or the direction x, horizontal axis, and this blue line indicates the temperature profile. T is temperature is function of x. How temperature is varying as you vary x. So T into bracket x indicates temperature is function of x, and this blue line is the temperature profile, you can call it as. Fine. And I am taking one point here, and I want to know what is the direction of heat flow here, right? So I have to find out what is the temperature gradient first. So for that, I am just drawing one tangent at this point. This is the tangent, and then I am noting down this deltas. Delta x horizontal, this delta, and delta t is the vertical. And what I observe in this diagram is both delta t and delta x are positive. Delta t is positive, delta x is also positive. So in short, this temperature gradient dt by dx is positive. This is what I am saying. Look at the nature of the curve. Clear? Hello?
Yes, sir.
Now look at the other diagram on the right hand side. So you have this kind of the temperature profile now, right? And again I am taking one point and drawing the tangent like this, and then I am noting down the deltas. So now this time I find this delta x is positive, but delta t is negative. This delta t is negative now. And then I'll write that dt by dx is negative. The temperature gradient is negative now. Fine?
Sir, here is direction of heat flow, sir. So what is the significance of that, sir?
I'll talk about it. You first note down this. Have you noted down this?
Just a
Yes, sir.
minute, sir. We are drawing.
And at the top you write your the Fourier's equation also. That Qx is minus Ka dt by dx.
Sir,
Bolo.
so the second
What
delta t is negative. In the
Huh?
second diagram, delta t is negative. In the first diagram, delta x is also negative, na? In the first diagram.
Look at the curve. Look at the nature of the curve. No? See, when you are drawing the tangent here, no? See, I am going in this direction for the x, so it is positive, no? But I am going downward in case of temperature, so this is negative. Getting me or not? And in this case,
Yes, sir. So
I am going in positive x direction, and here also I am going in positive t direction. So both are positive in this case. Here, the delta x is positive, but delta t is negative. Clear?
sir, in the first case, delta x, we are going from right to left. So the x is decreasing.
No. See, I have shown the direction here. No? See, look at the slope. So this is positive slope, no?
Or he's asking, sir, the direction of the heat flow is from right to left.
Don't
why
try. Hello. Don't try to mix the direction right now. Have you understood these conventions? Minus, plus, first of all. Have you understood this?
Yes.
So just note down that in this case the temperature gradient is positive, and in this case it is negative. Bas itna note down karo. Then I will talk about the direction of heat flow. Have you noted down this first?
Yes, sir.
Now try to use this expression for this case, let us say. So we know that dt by dx is going to be negative, right? This case. So if I put that minus sign here for dt by dx, or minus sign I'll get for dt by dx. So this minus will become plus, right? So qx will be plus, correct? Qx will be plus. Get him or not? Hello?
Sir, can you please repeat once?
Sir, can you please explain once again?
See, if dt by dx is negative, I am going to use the negative sign here, no? So that negative sign and this negative sign will become plus. Minus will become plus. So qx will become plus, no? Positive, no? So that is what I am writing here. Qx will be positive. Correct?
यस सर अभी क्लियर हो गया मतलब सर राइट साइड में सर मतलब qx पॉजिटिव रहेगा और यहाँ पे नेगेटिव रहेगा लेफ्ट साइड.
Now understand what I made the statement in last slide. Why we are putting minus sign? Because we want qx positive in positive x direction. Now don't you understand this? The direction of the heat flow is positive in positive x direction. So this expression is as it is applicable for this case or not?
Yes, sir.
Yes,
So
sir.
x is positive in positive x direction. Now try to apply the same to this case and tell me what happens. Left hand side curve.
सर वहाँ पे
Sir-
QX नेगेटिव आएगा.
हाँ. So this case QX will be negative. Now what this QX negative indicates? The direction of heat flow is opposite to
डायरेक्शन ऑफ x मतलब x के अपोजिट है उसका. यस सर, समझा सर, समझा.
again.
यस सर, वी गॉट इट.
And also try to understand that the heat transfer direction is always from high temperature to low temperature. So look at this. It is in this direction. Temperature will be higher on this end and it is lower on this end, right? So the direction of heat flow will be in this direction. Here the direction of
So
heat flow
sir,
will
it
be
means sir,
in this
so if
direction.
the direction of heat flow is in the direction of displacement, so in that case positive, or in opposite direction, so negative, na sir?
See, the direction of heat flow will be always from high temperature to low temperature. Clear?
हाँ sir.
How it is. See, if you are using the formulas to find out the rate of heat transfer Q, let us take the example. The best way to explain this is, let us take a steam pipe like this, and steam is flowing through this pipe, right? So we know the direction of heat transfer will be from steam to the surrounding, na? This is Q, right? The rate of heat transfer or the direction of heat transfer will be from steam to the surrounding. And this is the R direction, which is positive direction. The radial direction I am saying is positive, I am assuming. So for this case, the Q value will be automatically positive, right? Get me or not?
Yes, sir.
हाँ sir.
Now,
Yes.
now the same formulas I may use for the another situation where we have the cryogenic fluid inside this pipe, which is at low temperature compared to the temperature of the surrounding. Now in this case, what will happen? The direction of heat flow will be from outside to inside, right?
Yes, sir.
So in this case, when you use the formula, you will get the value of Q negative. And what is the significance of this negative sign, Q negative? It means you assume that the heat transfer direction is radially outward, but now you are getting it radially inward. So that minus sign for Q indicates that the heat transfer is taking place from surrounding to the fluid which is there inside the pipe. And in both cases you will find the direction of heat transfer is always from high temperature to low temperature. Does it make
Sir,
sense now?
Yes sir. Sir, it is in accordance with the sign convention we learned in thermodynamics, no sir? Yes.
It is in line with whatever the conventions we have used previously. So one thing you should remember here, why minus sign is used there in the Fourier's law? It is not the sign for K, remember.
Sir,
Ah.
sir, as in the second diagram, delta
Ah.
T is negative. Likewise, in the first diagram, delta T and delta X both should be negative, na? Because both are decreasing.
No. See how they are decreasing, you are saying. They are increasing. No? You have to look from this side, no? Or not?
Sir, for the direction, we have to look to the direction of heat flow, na? From
Which direction you are
initial state to
direction
final
of
state.
heat flow you are saying?
Yes, initial to final state, na?
See, you have to look at this direction axis when you talk about the initial to final. Final to initial. Get me or not? Okay, I'll explain it with different diagram. Let us say you have the slab like this, okay? And this is temperature T1 and this is temperature T2. Fine. And I'm writing here T1 is greater than T2, right? And assuming the linear temperature distribution, the temperature profile will look like this, right? Will look like this, correct? And now this is my X direction. I'm measuring X in this way. Clear? Now I'll write dt by dx. Tell me. I'll write dt by dx. Let us say this is L. I'll write dt by dx.
T2 minus T1
See, I have
upon.
to look at this X, no? So it should be T2 minus T1 divided by L, no? or not?
Yes, sir.
Okay,
Yes.
now different situation. Now same slab is there. I am still measuring X here. And now this time I will say this T2 is greater than T1. So how the temperature profile will look like? It will look like this, right? It will look like this, yeah.
Yes, sir.
Now in this case the temperature gradient was negative. But in this case temperature gradient will be positive. So don't you see the similarity between these two and these two curves? So this is more like this curve, and this curve is more like this. Have you understood it or not?
With respect to origin solve करना रहता ना हमेशा.
You have to take into account this sign, this direction. There is one example, there is one numerical based on this sign convention, which we are going to solve maybe next lecture at 11:20 we will solve, and then it will be more clear to you that there should not be any kind of confusion how we decide the direction of it. No? So three things are involved here, that is the heat flux, then the temperature gradient dt by dx, and the direction x. So how these three are interrelated, we will see in the next lecture at 11:20. There is example based on this.
Hello, sir.
Bole.
So we are always going in positive x direction.
No, not necessary. I am going to change this direction now afterwards. Just a minute. See, what I am trying to say is I may use different kind of conventions. Now we are talking about this kind of plane, na? Correct? So I may use x, positive x in this direction also. I am going to change the orientation of the axis, and then also our principle is going to remain one and the same. This we will demonstrate using example in the next lecture. Fine? Is it clear? I think we are running out of time. Let me just take down your attendance first.
Yes,
and
sir.
we'll come back at 11:20 and we'll continue our discussion hereafter. Just let me stop the recording.